All right, good morning, everyone. Welcome, everybody, to the third day of our Net Zero Research Conference. I'm Dr. Andy Smallbone. I'm an Associate Professor at Durham, and I'm the Director of the Decarbonising of Heating and Cooling Network. And I'm going to be chairing today's session and tomorrow as well. The next 2 days are structured around the themes of the EPSRC network for the decarbonisation of heating and cooling. I guess the last 2 days have been principally about hydrogen, and particularly about hydrogen in for transport, but now we're moving over to heat and cooling more specifically. So over the next 2 days, we're going to be looking at the challenges across different sources of heating and the challenges faced by different sectors in meeting their net zero aims. I'll give you a quick explanation about what the network is, and then we'll move into the sessions. So we've only really recently launched the Network Plus on heating and cooling. And I guess the first question that everyone asks is, what is a Network Plus? So the UK research councils have established this kind of framework of Network Pluses. They've been created to provide an impact and dissemination platform for the many projects that the UKRI funds. They're extremely important mechanism for bringing UK industry together from academia all the way through to industry, in order to make sure that everyone knows that all of these hundreds of millions of pounds worth of projects, everyone knows that they're going on, and that information is shared. So what we've got is a dedicated team to organise dissemination engagement activities and support those projects. And we have other roles like taking some kind of leadership role in leading what's happening in that particular area. And our challenge is the decarbonisation of heating and cooling. And I should also note there are other Network Pluses across challenges like transport, bioenergy, energy storage, etc., etc. The last 2 days have been about one of those in transport, which is obviously hydrogen transport technology. Who are Network Pluses for? Well, I think across these 8 different titles here, it's for everyone. Principally, I guess, about research and academia and people involved in technology and social science. But in general, actually, there should be an event funded through our network, which is relevant to everyone, all the way through to the general public. And in reflecting that, the fact that it's all paid for by UK Research Council, it's free for anyone who wants to attend our activities. There's no official membership, there's no membership fee, just sign up, come along. Obviously in lockdown, most stuff has happened in the online domain, but hopefully we'll be transitioning to face-to-face stuff in good time. The Network Plus is being led by Durham, Oxford, Brunel, Heriot-Watt, Leeds and Northumbria, and is supported and initially set up with lots of organisations supporting the application, but it's really for everyone. We might be leading it, but events and activities and speakers and so on, they're all from all over different places internationally and across the UK. We have a number of kind of core objectives. The first is to grow a world-leading UK-based research network around the topic of thermal energy, and that isn't tied to any particular objective, in the sense that it's just supposed to support net zero carbon heating and cooling, and also it's for residential, business and industrial sectors. It's not tied to anyone specifically. We aim to bring together different kind of groups, whether they're technology developers, end users, social scientists and policymakers, and we're trying to get them to talk together, because this is a whole challenge. it's an integrated solution that will lead us to a net zero in heating and cooling. And we'll do that through a number of routes. We're talking about sandpits, workshops, opportunities for secondments and studies, and wider engagement activities. We also aim to try and do some cross-cutting and make some cross-cutting challenges via research and developing some consensus around them. And then we have some flexible funding. I guess this last point is really we have some funding to support doing these secondments, support doing some startup research activities and so on in order to do that, and also how to upskill our early career researchers so that we can keep the ideas coming. Across our 5 core themes, and these were constructed around all of the different areas that are relevant, and they're quite general. But the first one is really around what we've called primary engineering technologies and systems for decarbonisation. So this key theme is on the technical end of the scale. This is about heat pumps. This is about hydrogen heating systems and so on. The second theme here is underpinning technologies, materials, control, retrofit, and infrastructure. So these are the parts or the systems that enable you to heat or cool your home or your business. Third theme is around future energy systems and economics. So how does this fit in with the whole wider net zero challenge? Where does the energy come from for our next generation of heating systems and cooling systems? And how much will it cost? And how will that be enabled? And then themes 4 and 5, perhaps slightly less technical and more social science based. The first one being societal impact and how do end users perceive our transition to net zero, and how do we build those into our thinking. And then number 5 is more of a top-down, how do we support policy in making and enabling this, and how do we support leadership to make some of the difficult decisions that may need to be made in order to get us to net zero within the expected timeframes. Now, all of this will be done through the network platforms. We're planning to help do this through what we originally put in was 20 co-organized events, which would be conferences, sandpits, trainings, and workshops. This was obviously pre-COVID, so some of this is changing a little bit as we talk, but to give you an idea, there will be a lot of events in and around this topic. We will facilitate this through some secondments and travel bursaries when travel permits. And as I mentioned, there's some feasibility funding budget available, and that will be announced in due course. And we're also developing technology roadmaps, which should help us explain what the challenge is to a wider audience. Now, this is kind of my last slide before we start moving on to the talks, but we've got a number of different routes to push outreach. The best one and the most informed one is the Net Zero Research website. If you go to there, you can sign up and then you can get on the email list. If you're on the email list, you know when activities and they'll be pushed into your inbox. You can always go there and find out when the next event is. Over the last few months, we've been doing lots of webinars and so on. So, and you can also go back and look at the videos because everything was recorded, and that's all available on those different platforms. So now coming really on to the today. Today's topic is heat and energy systems. We're not sure if this was by design, but today is also Earth Day, and that today is a day to reflect on what we can do to help restore our planet. And this is obviously a very timely combination because heat and energy systems is possibly the UK's biggest challenge for reaching net zero. And we've basically structured today into 3 parts. What we're going to do now, we're going to have a question time session. The topic of the session is heat and energy system, which is the topic of the day. This afternoon, we will be hearing about, I guess, the 3 kind of core areas very topical, all three in heating and energy systems. Hydrogen, heat pumps, and cooling. Each speaker's been asked to present for around 20 minutes. We will now be able to connect up to the screen of Jenny Pudjianto. So Jenny is an advanced research fellow at Imperial with the expertise in energy system modeling and also optimization, and he leads the development of whole systems approach and has carried out studies for the Committee on Climate Change, as well as BEIS on evaluating a range of heat decarbonisation strategies. And these include hydrogen, electrification, hybrid systems, district heating, and other emerging technologies, such as the fuel cell and also thermal storage. And he's a senior member of the IEEE. And hopefully, Danny is now ready to talk to us about the role of hydrogen.
Thank you very much for the introductions, Andy, and also the invitation to speak. Can you hear me clearly, and can you see my screen? And
yeah, all ready to go.
Okay, that's good. Okay, good afternoon, everyone. So the research group at Imperial has been actively investigating or studying the heat decarbonization strategy, and especially with the focus also on the whole system approach, as we think that the integrated decarbonization, the strategy for decarbonizing heat has to be also integrated with the decarbonization of other energy factors like electricity and transport. But in particular here is that I will also focus on the role of hydrogen. And if you already noticed that the hydrogen there has got a number of different colors, and hopefully you will understand what that colors means by the end of the presentation. So this just to provide an overview of my presentation today. I will start with the background, just explaining very briefly the key challenges in decarbonizing heat, what are the options, and then the approach that we use to analyze this, and also to share with you some key findings on the studies, on different studies, and to summarize. So the which heat decarbonization strategy along with the electricity is the key question that we would like to address here. All scenarios of the studies related to the 2050 scenarios, so all projected demands, costs, available technology, and so on, are based on the 2050 and with the net zero emissions. This is consistent with the UK government target. I think it's also already discussed previously by Professor Taylor's in the morning sessions, and he summarized it very accurately that the heat, if you look at the diagram here, show that the heat demands and total heat and cooling is 657 terawatt hour. It's kind of more than 50% of the total annual energy demand, and this contribute around 30% of the carbon emissions. So, in order to decarbonize our energy system, and this has to be addressed definitely. But the problem with this is that while there is a kind of a clear direction on how to decarbonize electric and the transport, there is still quite a big disagreement on how heat will be decarbonized. And there are a number of options thought that is decarbonization heat through green gases with hydrogen, biogas, and so on, or with electrification using heat pumps and resistive heatings based on the renewable energy sources. There may be a combination with the hybrid heat pumps, and plus district heating, bioenergy, and combination of all of those technology plus something else. Something else can be a CHP, fuel cell, and so on. And the key challenges is, as you can see on the graph here, that the heat is very significantly larger than the electricity demand, and it also very seasonal. More heat during the winter and less during the summer. So the energy system has to be able to deal with that. Yeah, just to mention that this is kind of the input assumption here, but this exclude the energy demands that from technologies that will be optimized later on, for example, like from the electrolyzer, reformers, and direct air capture with storage. So how do we address those? Is that what we believe that the system will be more complex, intertwined in future, as you can see on the diagram on the left, that the energy system, the electricity, and with the gas, with the hydrogen, will be linked all together also, and this has to be kind of solved or optimized simultaneously or in a coordinated way. It's not, maybe it is more stronger need to go for the coordination compared than the present system. So we use the tool called IWES, Integrated Whole Energy System Model, to model all of those. And this also has got not only the interaction between the technologies, but also a different level of the system from the supply side, the transmission, and also the distribution up to at the end, at the demand side. And we also take into account, consider different various flexibility technology from demand side, flexible generation, the network, and also storage, and also the interchange between the UK, for example, with the Europe. So in the UK, we also model number of regions, 40 regions, according to the DNO regions. And the solution is not only capturing the capex, but also take into account a number of different time frames. For example, from the investment time horizons in years, to the of course seasons, days, hours, and even minutes. Especially, this is very important for the electricity system to be able to operate securely and having a sufficient reserve in the system to control the frequency. So the optimization, the IOS, in a nutshell, it is least cost optimization problems. It's to determine the investment and operation of the multi-energy system involving electricity, gas, including hydrogen, heating, and also the CCUS system, which is I think is very important role in future to meet the carbon target while maintaining the system security. There are a lot of input data assumptions needed by these optimization problems, from the load profiles, is hourly or half hourly, from the electricity, space heating, hot water transport, and also the temperature, which then determine the COP of the heat pump, for example. And it also takes into account a large number of technology from power generation, different technology power generation, network, hydrogen production technologies from the methane reformers, electrolysis, bioenergy, with and without CCS, hydrogen network, heating technologies like air source heat pump, ground source or water source heat pump, CHP, solar thermal, natural gas, and hydrogen boilers, hybrid district heating, and so on. And also energy storage and CCUS system, plus the demand response. And of course, there must be assumption on the capex and opex of all of those technologies, and the other constraint like the emission that need to be achieved, security criteria, and so on. But I think the important is the output data. So the output data from the model will provide us with the optimized multi-energy infrastructures, including capacity, where it's located, and the technologies, the portfolio, and so on. And how this is, all of those technologies will be operated in a coordinated manner. What are the capex and opex associated with those? The fuel usage, carbon capture and emission performance, energy exchange, capacity sharing across region, and also the flexibility deployment considering the sector coupling. So this is a kind of the first result that I would like to show to you. So we analyze here three kind of mainstream of how the heat can be decarbonized using the hydrogen boiler, primarily for the customer with the gas connections. But of course, for the off-gas lit customers, they need to use electric heating. That's the assumption in the study. The second one is the electrification. So all heat will be decarbonized through the use of the heat pump and resistive heating, and the combination of those using, but not using the hydrogen, but using the natural gas boiler is the hybrid system. And we have two kind of another scenarios here, whether the system is low flex and high flex. The low flex system means that the system doesn't have significant demand response, distributed storage, having a limited interconnection capacity. While with the high flex, it's allowed the model to invest on those technologies. And the y-axis here is the annual system cost, and you can see that there are a number of different cost components here showing on the right legend here, with the C expressed as a capex and the O is opex, and it is divided into the electricity generation, electricity network, the opex of electricity. This is the electric heating, capex, and the storage, and then after that is the infrastructure of the hydrogen, including the hydrogen production capacity, the CCS, the electrolyzers, hydrogen network, hydrogen storage, and so on. And this is the OPEX of the hydrogen and gas. And the orange one here is associated with the cost of the capital cost of the gas heating, and then hybrid heating and the district heating, and the use of the demand response, and also the revenue from the electricity export. So here the results show that in all cases that I think it's important to say that all heat decarbonization pathway can achieve net zero. I think that's the issue is only how much it costs. And in here that the hydrogen is quite competitive, because it's 105 billion per year, for example, we with the low flex, and then the electrification is higher, but lower with the hybrid. But of course, this depends on the assumption that we use in the study, because the other studies also show kind of a similar small differences between different the cost of different heat decarbonization pathway, which actually create a little bit more issue, because it is not clear what is the winning pathway here. But what is important to note in this study is that depending on the heat decarbonization pathway, that the infrastructure needed will be quite different. So this will require quite a clear direction on how how heat will be decarbonized in the future, because this will determine how this infrastructure will need to be built. I need just to be more quickly. So this is the result here show that there is also significant benefit of improved flexibility in all pathways, not only in the electrification, although the electrification is actually the one that need a significant flexibility from the demand response, for example, or the distributed storage with a smart EV, smart appliance, and so on. But the benefit of the enhanced flexibility also appear in all pathways, also in hydrogen pathways, for example, with around 10 billion pounds per year. And with the hybrid, it also, for example, the importance of the use of the gas just at the right time, that also will reduce significantly the cost. And why it's important, the flexibility in all pathways, because there is off-gas customers, of course, that use electric heating, but also that most of the electricity supply in future will be from the renewable, as we will see later on. And there is also an interplay between hydrogen and electricity to provide this low carbon energy and storage. So how the heat is supplied. So this left diagram here show that how the heat supply from in different pathways. With the hydrogen, of course, that is using the hydrogen boilers. In electrification, most of the heat is supplied by the heat pump, and with the hybrid combination, that the most is supplied by the heat pump, but some with the boilers. And in here, that all of the scenario using the same kind of district heating pathways. But it is interesting that when the system is quite high flexible, and then also the use of the smart hybrid heating system, then the use of the gas can be minimized here. But although it is used only very little, that it provides a significant value. as we have seen previously on the previous slide. So the question with the use of the unabated gas boiler, for example, is also, I think, expressed in concern with the CP6 report that it was not considered as an option, and because this will have a emission, and we can see this one clearly on the graph on the right hand side, where the emission from the heat, for example, is quite large. So the graph here show the emission from the hot decarbonized sectors and also residual emission from the electricity and also the reformers. But this will need to be offset by technologies that can be counted with the negative emission technologies, like with the bioenergy with the CCS, and also with the direct air capture with the CCS. Also, there are some very small hydrogen, for example, or combustion offset from the biomethane. But in the hybrid with the natural gas, this will require a significant larger direct air capture. But although having said that, the cost is still cheaper, it's still lower cost. So this means that the use of the CCS technologies, for example, including BECCS and DACs, let's enable all technologies, although maybe it's high carbon, to be deployed in order to minimize the cost. So maybe we can consider the use of this unabated gas heating, but if we have the technologies to offset the emissions. And how this hydrogen has been produced. So the graph on the left show the hydrogen production capacity, and it is interesting that most of the hydrogen capacity comes from the methane reformers. In here, we use the autothermal reformers with the CCS, and this produces the blue hydrogen. And this becomes quite, I think, the bulk of the hydrogen production is here. Show that it is coming from this methane reformer because it is lower cost. But there is a room for the electrolyzers, and although electrolyzer is more expensive, but the electrolyzer provides the system value, which then make it valuable to the system, and for example, in order to reduce the wind curtailment and so on. So this helps the integration of the electricity, and that's the reason why we think that it is important for heat decarbonization also to be quite integrated with the hydrogen, and on top of that, there will be some hydrogen produced from the biomass, and it can be maybe color is brown or something like that. And it's different. It's in the different the heat decarbonization pathway. There will be different mix of how the hydrogen is produced. And primarily in the ELEC and the hybrid, for example, that the hydrogen is also used for the industry. Okay. Another dimension to look at is that the impact of the flexibility here. That the flexibility actually increase the production from the thermal reformers and reduce the electrolyzer. And because the electrolyzer provides flexibility, if there is any other flexibility technologies that can compensate that, then the role of electrolyzer become less. But nevertheless, that you can still see that there is still a certain extent volume of electrolyzers to be included in the hydrogen mix. And I think the third graph show here is the amount of the hydrogen storage needed, and we see that with the hydrogen pathways, of course, then we require a significant large hydrogen storage just to make sure that we got a significant capability to provide the hydrogen during the peak demand, and also to bring over some energy, for example, if it is produced by PV on summers to the winter. But what we observe so far, that's actually relatively small, just to make sure. And now the question is that there's few whether the hydrogen should be produced by the electrolyzer, the green hydrogen. So in here we carry out study comparing with the optimal mix, and if the hydrogen is only produced by the by electrolyzers, and we see that that the cost increase significantly because of that, because again, this show that the system application is very important, because we will require a significant increase in the electricity investment in the low carbon electricity generation, but also investment in the electrolyzer. So having only a green hydrogen may be not feasible economically, because it will cost 19 billion more. So this is just deploying only green hydrogen and no CCS impact. So the model can be used to analyze what will be the impact. And here we can see clearly that this is the additional cost of having only the green hydrogen. So more low carbon power generation, more electrolyzer, more hydrogen storage, but you can compensate with the less cost of the ATR and heating generation, and also the OPEX from the gas. What we think is that what is important also finding is that the integration of hydrogen system and electricity, we also need to be facilitated. If you look at the middle one here, that the hydrogen or the electricity can be converted to hydrogen by electrolyzer, and the hydrogen also can be converted back to the electricity using the hydrogen power generation. So the question that we had in our study is that what will be the value of this coordination? So we carry out study with two case studies. One is with the silo approach, and one is with the integrated approach. And with the silo approach means that there is no electrolyzer, no hydrogen power generation. Well, with the integrated approach, we allow the model to propose electrolyzer and hydrogen for power. And we can see that in terms of the annual hydrogen demand, this will increase the hydrogen demand by 71 used in the hydrogen for power generation. And this is also reflected in the annual hydrogen production here, where the electrolyzers is actually produce a certain amount of the hydrogen. So there is an integration happening in the integrated approach, well, in the silo approach, that these both systems are planned separately. And I think maybe just concerned about time, I just put the cost here, that with the silo approach, that this will cost around 5.6 billion more. And this is associated with as you can see the impact here. This is associated with that in the silo approach, the OPEX of electricity will be higher because of the use of the gas CCUS, for example, while in the integrated approach, that the gas CCUS can be replaced by the use of the hydrogen for power, and also with the integrated approach, that it will require less carbon emission technologies, negative carbon offset technologies like DACs, require less natural gas usage and hydrogen storage. But of course, this will require a significant increase in the investment in the low carbon technology and also electrolyzers. And of course, there is also, if we look at the hydrogen, then one of the key sensitive factors for the hydrogen is the gas price. So we carried out study with the different gas prices, with the low, central, and high here, with the different assumption, and show that with the low gas prices, then of course the annual system cost will be lower, and with the higher gas prices it will be higher. But in here on the right-hand side diagram, you can see the impact of having low gas price. With the low gas price, that the system actually shift to use more hydrogen in the system, and then reduce the low carbon power generation, and then also reduce the use of the electrolyzers, because the gas is cheaper. But if the gas is high, then it is shift from the use of the hydrogen to low carbon power generation and the use of the electrolyzers. That's how I think it's quite expected results. So just to finalize my talk, that in summary, the hydrogen pathway is a potential option to decarbonize heat. Other alternatives can be also considered, for example, like with the hybrids and full electrification. But improving system flexibility will benefit all pathway, particularly the elect. But it's also it improves the or reduce the cost in the hydrogen pathway as well. There is a strong interplay between the hydrogen and electricity, and that's the reason why we need to have coordinated multi-energy system planning and operation in future. Because if the silo approach will actually lead to more costly system. Hydrogen system can provide flexibility, so there is a sector coupling flexibility from the hydrogen and electricity, and vice versa. Just to finish off that there's a strong interplay between hydrogen and electricity, and that's what we believe, that there is an importance of having coordinated multi-energy system planning and operation in future, stronger coordination compared than present practice at this moment. And we also has demonstrated that the hydrogen system can provide flexibility to the electricity system. There is a sector coupling flexibility that need to be harnessed through the electrolyzer and also the hydrogen for power, and the supporting environment for the hydrogen is low gas price and also the availability of the CCUS technologies. Thank you.
Brilliant. Thank you, Danny. I think, yeah, a lot to process there. A lot of things in your modeling included. Next, we're moving over to a talk around the topic of making heat pumps happen from Jenny Crawley from UCL. Jenny is a research associate in energy and buildings at UCL. She's the academic manager for the EPSRC funded Centers for Doctoral Training in Energy Demand and Energy Resilience and the Built Environment.
Great. Hi, everyone. Thank you so much for this invitation to give a talk about heat pumps. So my talk's called Making Heat Pumps Happen. And I'll just give a very brief introduction on behalf of UCL Energy Institute, where I work. So there's the office in central London on the left, although we've not been in there for a while. And I'm also part of the physical characterization of buildings group, which is primarily a physics group, but it has some socio-technical work going on too. And as Andrew said, I help manage 2 centres for doctoral training in energy demand and energy resilience. And as you can see on the bottom one, Irby, we're recruiting at the moment. So if you or anyone you know would like to come and do a PhD in how the built environment and energy resilience can be mutually beneficial, then please do apply. We've got some projects being advertised at the moment. Anyway, enough about me. What this talk is about. So I often find, especially in the modelling literature, that heat pumps get treated as a technology which can be just directly substituted into homes to replace what's there at the moment, which is normally a gas boiler. But I think what's a bit neglected is that heat pumps work very differently from boilers, and they interact differently with basically everything around them, with our homes, with the built environment, and with the wider energy system. And so integrating these quite different beasts into the system is going to be quite a challenge. Yet there is a lot of research going on regarding how heat pumps will fit into the system and what changes might need to be made to enable them. So I was asked to give a talk about the latest research, not necessarily our own, but recent developments in heat pumps. And I decided not to focus directly on the heat pumps themselves and their inner workings, their efficiency, but other considerations regarding how they interact with the rest of the system that need to be cracked if we want these things to be deployed at scale. I should also say there was a question earlier in the chat about individual versus district scale heat pumps, and I'm just going to focus on individual dwelling heat pumps today, just in the interest of time. But I do have a PhD student called Zach Wang that's looked into kind of costing up individual versus large heat pumps and heat networks. And I'm very happy to give you his contact details after this. He's about to have his Viva, so his thesis hasn't been made public yet, but he's been comparing the different options if you want to talk to him about kind of the relative strengths and weaknesses of where you put the heat pumps in the system. But I'm going to focus on individual ones today. So briefly, I'll talk about the interactions between heat pumps and ourselves, people, and with the electricity system and with our homes, the built environment. Okay, I thought I'd start with people because this is the one that tends to get maybe talked about less. in sort of technical sort of conferences. So where are we now? Just a few statistics. So it turns out that 57% of people know very little about the need to switch away from natural gas for heating. So this is our starting point, really. Not very much kind of motivation or awareness on that front. But when we kind of drill down specifically to heat pumps themselves, air source heat pumps, most people either haven't heard of them or have heard of them but don't know what they are. Okay, again, not a great starting point. Indicates there might be a bit of a problem. I think it gets worse. If you divide that by gender, men tend to know a bit more, but women, my species, we don't know what heat pumps are. We know even less than men. 2/3 of us don't know what they are, or we've heard of them, or we might not have heard of them. Also, awareness of heat pumps increases with social grade, so that those in the kind of lower socioeconomic groups are less likely to know what a heat pump is. So I think from this, our starting point is we're in a place where there is lots of work to be done if we do want heat pumps to be adopted at scale. Okay, here's some references for those numbers. But what could be done? So this is quite interesting. We're told by the social researchers that people don't necessarily care what sort of heating system they have in terms of what type it is, but they do care a lot more about the quality of their heating experiences. So what do we mean by quality? Well, specifically, people mean they care about how warm and comfortable they can get, and they care about the convenience of operating the system, and they obviously care a lot about the cost. And what this tells us is that if heat pumps can perform equally or better to what people have in their homes already, then potentially they are kind of they are acceptable to people, because people don't really care that it's a heat pump or it's a boiler, as long as these criteria are met. Okay, so there is potential. Just a bit of fun here. My colleague Mike Fell has developed Pump Chic, which is a website where you rate different heat pumps in terms of whether they're hot or not. And the kind of serious point behind this is that if heat pumps are going to be deployed at scale, they need to be integrated in a way that looks good and that is acceptable visually as well. So he's trying to find some beautiful ones, and people can decide kind of how they're landscaped and whether they look nice or not. Okay. So we'll move on to the relationship between heat pumps and the electricity system. And I think Peter Taylor gave a really excellent introduction to this morning, actually, if you were there for that. But the two main problems around this is the potential for the peak demand increase at both a local and a national grid scale, and the sort of total annual electricity demand increase. And there's a third potential problem, which is called ramp rate. But actually, I think recent work has shown that this isn't so much of a problem. So we're just going to focus on these two. And just as Peter was saying this morning, and we'll prove it in a minute, the nature of these two problems really both depend on how heat pumps are used. And I think it's really important to say that heat demand is not some kind of fixed external exogenous platonic thing that just exists, but it does vary according to which technology provides it. And so we did some work a few years ago comparing the sort of profiles you get from heat pumps and boilers, showing how much less peaky the heat pump profiles are compared to the boiler profiles. These have both been normalized against their peak. And I think basically you need to, when you're thinking about modeling heat pumps and modeling boilers, you really need to use the sort of most recent and best evidence on how they're actually used and how that aggregates, and not just kind of take a generic heat demand profile, because I don't think that actually exists. It's very much a function of the technology used. Otherwise, you can come up with some really, I think, results that are really out in terms of how much of a problem different technologies are going to cause for the electricity system. So Peter referred to Stephen Watson's work this morning. This is just going into a bit more detail about, well, what is heat demand like from heat pumps and what's its shape. And in the most recent large-scale field trial, which was the RHPP field trial, it's been found by Stephen actually that over half of people were using the heat pumps, what he called continuously, which isn't quite continuous in these graphs, but it's kind of more or less on all the time. And again, why is that? Well, that's also a function of all sorts of things about how they've been installed into the homes, what kind of advice the homeowners had, how people have kind of adopted those and are living with them. And I think this is probably a sort of worst case scenario for the future, because in this particular trial, a lot of the heat pumps were put into social housing, and I think basically people operated them like they do boilers, which we might not necessarily expect in the future. Anyway, so when these sort of profiles are all added together, including the people who ran them all day at the top and the people who ran them a bit like boilers in the middle, you arrive at this graph on the right, which is to do with the shape of current demand for electricity from heat pumps. And as you can see, it still has two peaks, one in the morning and one in the evening. These peaks aren't half as bad as what you get from boilers, but nevertheless, they are still there, and the system is still going to have to deal with them. So now we understand the nature of the peak demand problem a little bit. Stephen, in his thesis, actually, did some work on adding this peak demand to the GB electricity system. And kind of to be quite brief about it, what he found is that peak demand is more than doubled, and annual demand goes up by a factor of less than 2. But these are very huge numbers we're talking about. So in his work, he kind of used this extreme example of 100% individual heat pump uptake, which clearly isn't that likely, but at least it gives us a kind of boundary of the problem, and we see this kind of doubling of peak demand, and we see how much extra electricity that would require, given these, I think, fairly realistic demand profiles that he's kind of used real data to provide. So that's the problem kind of quantified, I think, at its in the extreme of 100% heat pump uptake. So we've got this peak demand problem and this annual electricity demand problem. We'll talk about the peak one first, and how will peak demand be met if heat pumps are deployed en masse. So your first option is to meet the peak, and your second option is to reduce the peak. And Danny talked about this a bit in his talk as well, the value of flexibility in the energy system. So you can either reduce the peak by using a different fuel, so hybrids at peak times, or you can go down the route of load shifting and heat storage and doing fancy things where you turn the heat pump on and off at different times and store heat in various ways to make sure that people are still warm. And although I don't have time to go into a kind of proper full discussion of all the latest research around this, I sort of thought it'd be helpful to bring out some kind of main messages from the literature around these things. And I think one of the main messages is that these options both have quite good technical potential, but interestingly, they're probably going to involve some degree of automation in a way that when we run our current heating systems, we do tend to have a bit more control about how they're run. Whereas with turning things on and off to optimize when we can integrate kind of renewable electricity into the system, we're not going to be bothered to do that. Something's going to have to automate it. But we've been finding in some of our recent work about people that if control is taken away from the householder, then actually when residents do get involved, it can actually muck things up. It can actually compromise the peak demand reduction. And that's a really hard dilemma, because you don't really want a situation where when people are empowered and engaged to get involved, they actually make things worse. It doesn't seem like a really good way of doing things. You kind of want the people in the system to work together. So I think that's a bit of an unsolved problem, really. The other thing is a lot of these scenarios rely on heat being generated by heat pumps at times when there's lots of cheap renewable supply and low demand, and some of them involve heat pumps being on at night. And actually, this is something that we take for granted, but research has found that if you do run heat pumps at night and try and charge the thermal mass of the building specifically, people get too hot. So don't rely on being able to do this. If you've got purpose-built storage where you can do this kind of thing, I'm fine. But if you're trying to just rely on the thermal mass of the house, then it doesn't always work. People do complain about being too hot. So that's just a very quick smattering of work on how to meet peak demand. It's very much a socio-technical problem. It's not just a technical optimization issue. It's how people get involved, and the things that might benefit them are actually causing quite a lot of disruption in their lives. So the annual demand problem, and this, where is all this extra low carbon electricity going to come from? And as I said this morning, I'm very much not an expert on this. I don't really have the right to talk about this. So I asked my modelling colleagues, and one thing that I do kind of acknowledge is there's no point answering this question without considering other ways that the electricity demand is massively going to change. So namely transport, basically. So we're looking to electrify large parts of heat and most of transport, and there's no point considering them on their own. So when you consider the kind of anticipated future electricity increase from heating and from transport, a number of people have attempted this problem of where's the low carbon electricity going to come from. Danny's team have done one analysis. My colleagues at UCL have done a different analysis. And so this is Dr. Price's analysis with an 80% renewable share and with a kind of largely heat pump heated scenario. And his model, which is called HiRes, has predicted that it'll be primarily wind and solar that are going to be providing the electricity. And there is some natural gas in there, and it mostly does have carbon capture and storage. And then even that on its own isn't quite going to be able to meet these kind of two different types of peaks, the daily one and the seasonal one. So his scenario has batteries charging and discharging to meet the daily peaks, and to meet the seasonal peaks. It's not actually shown here, but his view is that it's going to be basically PV generating hydrogen and storing it storing it for use in the winter. Because I think for me the winter versus summer problem in the discrepancy is probably a bigger problem than the kind of daily peak versus the daily average. I think the jury is still a little bit out on where the electricity is going to come from, but kind of here's one scenario in the literature of how it could feasibly be done. Right, and finally, I will talk about our homes and the interaction between heat pumps and real buildings. And I think the two problems that emerge here in the literature are, do we have to replace all our radiators because heat pumps like outputting at a low temperature? So do we have to have more radiator surface area? And then something that caused a lot of debate this morning, how thermally efficient do our buildings need to be? And I think the kind of main conclusion on these two is there's no clear answer to these, actually. There's a lot of opinions and no kind of definitive clear answers. And I'll give you a few examples of opinions from the literature. So on the radiators question, there has been some recent work looking into this because it is pretty important. It might add quite a lot to the cost if we do have to replace radiators. I should say that the research that has been done hasn't been a kind of directly answering the question because they weren't able to look at actual flow temperatures in heating systems and whether existing radiators can deal with low flow temperatures and provide enough heat. So they didn't answer it in that direct way, but what they did do is they got a load of EPC assessors to measure basically the size of radiators and physical size. And they estimated from that kind of suitability for installing heat pumps. And according to that research, only 10% of dwellings in the UK are already suitable for heat pumps if we run them at 55 degrees, and 1% are suitable for heat pumps at 45 degrees. But we at UCL are looking to do some research into this, which maybe answers the question more directly by looking at the real flow temperatures, especially when heating systems are used continuously, which is how we expect heat pumps to be run more and more in the future. So we'll be able to provide a better answer to that in a year or two's time. So on the thermal efficiency of the buildings, again, people argue about this. And actually the most recent German field trial, which I've written is from the year 20,210, but I hope you can realise this is supposed to write 2021 there. They concluded that it's actually not necessary to renovate their buildings to make heat pumps run efficiently. And they looked at flow temperatures of heat pumps installed in existing buildings, and they found that they were mostly quite low, but only occasionally quite high. I think the thing that makes it a bit hard to extrapolate their findings to our situation is that they call buildings old when they're basically from just after the Second World War. So their oldest building in there was from 1949, but they didn't have any really old kind of Victorian or older properties like we have. We haven't really done the study empirically properly in the UK, but from model results, our model results are different, and it's recommended that there is quite a lot of thermal efficiency improvements regarding insulation and glazing. But I would say, again, this question really needs to be looked at more empirically, and there's lots of examples of heat pumps being installed in actually really old Victorian houses at the moment to kind of demonstrate they do work. But equally, there's the other side of the debate, which says, yeah, the more fabric work you can do first, the better. More research needed on that, really, I think. So just to summarise, if we are looking at integrating heat pumps into our energy system at a large scale, the first thing we need to do is make sure that people actually know what heat pumps are. Sounds very obvious. We do need heat pumps to provide as good or better comfort, convenience and cost than current heating systems. I don't think that's impossible. I just think we need to make sure that they do deliver to the consumer. We do need a lot of extra renewable electricity, and I do think we need some seasonal energy storage. If we're going to look at these strategies like demand shifting and peak load reduction, I do also think we're going to need the buy-in from householders, really engaging the occupants there. We do, I think, need some energy efficiency improvements of buildings, but it's really not clear to me how much we should do that before we get started with the rollout of the heat pumps. And then more research needed regarding whether we need to upgrade the radiators or not. So that's not answered all the questions, but hopefully that's given kind of a little bit of a smattering of the literature on some of the main questions around integrating heat pumps into the system. Thanks very much.
Thank you, Jenny. Thanks very much. Next up, we've got Professor Judith Evans. So Judith is a researcher in air conditioning and refrigeration at London South Bank. She works on food refrigeration operations throughout the food cold chain, from harvest, slaughter, all the way through to the consumer. She previously worked for the Food Refrigeration and Process Engineering Research Centre at the University of Bristol, where she was a senior research fellow. Before then, Judith worked for the Meat Research Institute and AFRC Institute of Food Research. So, Judith, can you hear us? Yes, we can see your video, and we can hear you, and we can see your slides. So
fantastic.
So please take it away.
Sorry, far too many acronyms. Hi, I'm Judith Evans. As I was introduced, I'm professor at London South Bank University, part of the School of Engineering and part of the Heating and Cooling Group, which is a group within the school. I'm going to talk about the food cold chain and concentrate on net zero. So just to give people a bit of a background on the food industry and to really stress that it is quite an important sector. It's the largest manufacturing sector in the UK. People may or may not be surprised to know it's responsible for about 176 megatons of CO2 equivalent emissions, and it's worth about 120 billion a year. It amounts to about 9.4% of gross value added, and it's a big employer. There's about 4 million jobs in the sector, 3 million in food retailing and catering, and particularly in food manufacturing, the number of SMEs in the sector is incredibly high. If you're talking about food production, Food and Drink Association estimate that 96% of the companies are small or micro SMEs. So it's often dominated by quite small players, although there are also some very big players in the market as well, your Unilevers, Nestle's, etc. It's got environmental impact, not only through the energy that's used, but also through the water, through food waste as well, and also through road freight. And the actual amount of greenhouse gas emissions that are associated with food refrigeration is actually not very well quantified at all. It's estimated by Carbon Trust that it's between 2 and 4% of the UK's total greenhouse gas emissions, but that really is a figure that's not well quantified at all. So in terms of the UK situation with food, the UK is actually relatively dependent on imports. If you look at these figures, which are basically from government statistics, this graph here shows over time the percentage of food that the UK can actually produce. This is potentially the food, this is the food that's produced in the UK that we could potentially eat. So we could produce 64% of all the food that we need. However, what actually happens is that we export some of that food. So we end up providing about 55% of the food we consume. And there's quite a lot of food that we import, particularly fruit and vegetables. So this actually makes the UK relatively vulnerable. You can also see in terms of what we produce, it has changed in some areas over time. This is showing from 1990 up to 2019 on a relative index, say taking 1990 as 100. You can see in terms of poultry, we've actually increased production over time. But in terms of potatoes, which is the grey line here, we've actually reduced production. And you can see that on most products, we've been sort of bubbling around that 100 baseline figure. And in some cases, we've reduced slightly. In other cases, we've increased. But apart from poultry and maybe potatoes, there hasn't been a huge change in what we produce over the years since, over the last 30 years. So the UK does have a food security issue. In developed countries, about 30% of food is temperature managed at some point during its life. But actually globally, only 15% of the food that benefit from refrigeration is actually refrigerated. And that actually means that you end up with quite a lot of food that gets lost either at the beginning of the cold chain or wasted at the consumer end of the cold chain. So about 30% of perishable food is lost, mainly in developing countries due to the absence of cold chains. And probably another 30% is lost as food wasted in developed countries at the other end of the cold chain. And that accounts to a huge amount of food waste. But it's not only the carbon that's associated with that food waste, it's also the impact on the natural resources, which is including land and water, that you're also wasting. So in terms of the UK has a target to reach net zero by 2050. We've got a target to reach 68% by greater than 68% by 2030 compared to 1990 levels. And since the 20th of this month, we've got a target to reach 78% by 2035. But it's all very well talking about net zero. You can see on the graph here, I should stress that this is all emissions and it's not just exclusively food, but it applies to food as well, which shows over time since 1990 our carbon emissions. And if you look at the territorial emissions, you can see that over time we've actually almost halved our territorial emissions, which means the emissions that were in the UK territory. But if we look at the actual emissions, which are consumption emissions, which are the blue line, those are basically the emissions that we import minus the emissions we export. You can see that it has changed over time, but basically it hasn't changed to a great deal. And the output from this is really that much of our emissions are actually exported and so come from abroad but aren't counted in our net zero. So if we are going to be net zero, it's all very well the UK being net zero, and that's great, but we also have to look at what happens in other countries and also encourage other countries to commit to net zero as well. We have to also be clear what the target is. because there's lots of targets about being net zero or reaching certain percentages by different years. But within the food cold chain, it's not very clear what your baseline actually is. We know that the UK has an electricity demand of about 346 terawatt hours in 2019. And that if you look at industry, that's about 27%. And of that, 13% is related to food generally, and that's about 3.5% of total. But that actually excludes the domestic part of the pie chart and the commercial part here. And you've got to remember that you've got domestic refrigeration, which at the moment is still a reasonable amount of domestic energy, and commercial refrigeration, where refrigeration is a relatively large part of commercial refrigeration. We do know from people like Food and Drink Federation and information from Duke's Digest of UK Energy Statistics that emissions fallen in food manufacturing. They estimate by about 42% between 1990 and 2015. And at the same time, the industry grew. So there has been some significant decarbonisation within the food industry. But the actual impact that refrigeration has is actually quite poorly quantified, because those figures are for all production and not just refrigeration. So these are some of the questions that we're beginning to try to investigate. We've got 2 new projects that we're starting to work on, looking at sustainable cold chains, which is a UCOAT project, and another EPSRC project, which is looking at zero energy cold chains. And these involve ourselves at LSBU, University of Birmingham, Heriot Watt, and in one case Cranfield also as well. And, you know, our first activity is to try and actually benchmark the refrigerated food cold chain for 2020. And then, as other initiatives, we're assessing what options there are in terms of technologies, which are available now and might be available in the near future to actually apply to forward look at how we could achieve that zero target in 2050. And I should stress also, it's not just the importance of maybe reaching the zero carbon, it's the rate that we do it as well, and the amount of carbon we're producing along the way. But it includes not just technical analysis, but it also includes non-technical and applying predicted changes, you know, such as those to climate policy, population, etc. And that's some of the work that will be done by some of the other partners in the projects. And, you know, one of the ideas is also to try and compare top-down, bottom-up approaches to looking at the carbon emissions to see whether we get any level of agreement. And as part of the project, we got support from quite a few trade associations across the whole of the food cold chain and organisations that have promised us information from their members. So we're hoping that we will get some really nice and new data as part of the projects. I should say one of the things about benchmarking is we need to be relatively careful. 2020 was not your typical year. And you can see in these graphs here that this on the left side is showing the volume of food that was bought over time, and the change in the blue bars from the previous year, 1919 to 2020. And you can see in terms of the volume, people bought a lot of food before lockdown, very little around lockdown, and then it sort of more or less returned to a slightly higher level because probably people were eating more at home and less out. And in terms of the right-hand graph, you can see again its volume of food, and you can also see that people carried out more trips to shopping before lockdown, and that's gradually been creeping up since. And also people bought more per trip, which is quite reasonable as there was less trips. So maybe on average it doesn't make so much difference in terms of the volume because we're looking at over a whole year, but we do have to be careful where we do apply our benchmarks, as it could seriously cause our data to be off kilter. So how do we reach net zero? There's lots of ways that we can do it. We can reduce the need for cooling, shift, improve and aggregate. And I was going to show you a few examples from each of these within the time allocated. There's not time to go into too much detail, but I tried to draw out a few interesting examples. And also, I ought to just say something about emissions, in that in food refrigeration, the carbon emissions generally originate from direct or indirect effects. The direct effects are mainly refrigerant leakage, and the indirect are from electricity. And there's a number of challenges, particularly in refrigeration. This is a typical sort of refrigeration chart, which shows flammability and toxicity, and refrigerants are actually classed by different letters and numbering categories. And traditionally, we've been down in this A1 area, which is low flammability or no flammability, and low toxicity. And so traditionally, we've been using these sort of refrigerants that are relatively easy to use and have got not many associated safety issues. But we're now moving up more to these sort of refrigerants, either to A2Ls or A3s, which are highly flammable. We've always used B1 refrigerants such as ammonia, but there's more emphasis perhaps on using those sort of refrigerants because they're low GWP. And technically, it's very difficult to get a low GWP refrigerant that's not flammable. So we have to be looking at different ways of applying refrigeration and managing it in the future. And, most of these technologies can be applied. We're not necessarily talking about amazingly new technologies. Technologies like ammonia refrigeration have been around for a long period of time. Things like using CO2 are slightly newer, but the application of A2L refrigerants, which are mildly flammable, is a relatively new innovation within the industry. So if we're going to actually try and reduce the carbon that we emit, it's not just a technical issue, it's a non-technical issue as well. And behaviour policy and business drivers are involved. You also have to remember things like training and maintenance as part of the non-technical issues, which swerve across also into the technical side as well. As a good example, doors on cabinets in supermarkets is actually quite a good example. This is some work we did a few years ago looking at a typical supermarket. So this is showing the carbon emissions that could be reduced in a typical medium to large size supermarket in the UK. So the size of the bubbles is actually the amount of carbon that we could save by applying a technology. This is just some of the technologies. We looked at about 80, 90 different technologies in all. And the graphs then show the uptake, how long it will take to actually apply that technology, and the payback as well, which includes not just the cost of the technology, but the installation costs as well. And you can see where you need to be is somewhere as close to this corner of the graph as possible, and with the biggest bubble that you can get. And so your eye gets immediately drawn to the pink bubble because the uptake time's very short, the payback time's very good as well, and you've got a pretty big bubble. I should also mention is that when we have colours and we have two bubbles of the same colour, it shows the minimum and the maximum, because in many cases there's quite a high level of uncertainty on the application of a technology, because this work involved looking at a lot of peer-reviewed publications and available information, and we also tried to rank the quality of the information that we got, which in some cases verges from being absolutely accurate and very, very good down to not very much information whatsoever. So if you look at the pink line, that's strip curtains, and it seems the obvious thing to do, but no supermarket is going to put strip curtains on their cabinets because they see them as a barrier, and they see that consumers don't like them. They get dirty and get damaged. So what supermarkets are actually doing are actually putting air deflectors or air guides on their cabinets, which again, it's down in that bottom left of the graph, but much less carbon savings. So they're making a choice that's based on, behaviour and social aspects rather than technical aspects. And really, probably what they should be doing is putting doors on cabinets. And these two, the mustard and the dark blue, show two options for glazing. One is putting glazing on the medium temperature chilled cabinets. This is also beefing up the doors on the freezers as well, in addition. So you can see that, what supermarkets are doing isn't actually necessarily what they could do. But it may be that in the future, things like energy labelling, which came in earlier this year, may have an impact on display cabinets. And there may also be policies in other countries. There are policies which encourage or enforce supermarkets to put doors on display cabinets. So it's quite a complicated issue, and choices are not always made on just technical merit alone. In terms of shifting, energy storage is one option, and there's a whole load of different options that are available, and I know some of them we talked about earlier. On the whole, most of the technologies that are being worked on involve latent heat storage or sensible heat storage, so they're in the thermal area. There's some work that's sort of on the periphery of food refrigeration, which is looking at mechanical storage, but otherwise very much at the moment, it's very much in the sort of battery area. But also food itself can be used as a battery, and that fits in very well with demand side response. Demand side response is already sort of used in cold stores. It's basically been used for a long time as arbitrage in cold stores, where they switch the cold store off at peak grid demand times. But it's coming more now into demand side response sort of approach. And recently supermarkets have also started getting involved in DSR. There was quite a lot of work done a few years ago on looking at DSR for domestic fridges. Because although domestic fridges themselves don't use a huge amount of energy, when they're combined up and everybody in the country has 1 or 2 refrigerators in the house, it makes a huge impact by being able to switch them off. But there was a lot of public kickback against something like that. So again, it's not just a technical issue, it's also a social technical issue. And maybe even so, you still need tariffs to incentivize these actions. In terms of improving, new technologies are great, but often there's a limited window when technologies can be applied. For example, cold stores are often replaced only every 30, 40 years. And so you have distinct windows of opportunity when you can apply technologies. And on the whole, most changes tend to be incremental rather than a step change. You very rarely go straight from the square to the circle. You go through all these other shapes first. And also, it's the case that in refrigeration, many technologies have been under development for a long time, and they're still not necessarily at the market stage. And you do have to remember that, on the whole, with most food refrigeration technologies, that most of the carbon is still embedded in the usage phase. As you make things more efficient, obviously that percentage does reduce, but it's still a very high level, and so the impact during the life of the system is still the most important thing. There's obviously other options as well that may be likely to be more in the future, which is fully integrating food systems into a grid or system. Work's been done by people like Danfoss, for example, who've integrated supermarkets into a heating and cooling network. And so this may be ultimately the future of quite a few of the cold chain areas. There's quite a lot of heat that's rejected from refrigeration systems. And so if you're starting to apply 5th generation heat networks, they are much more applicable than they would have been to earlier generation heat networks. There's also new business models, things like cooling as a service, where people aggregate together services and basically sell cooling. And this is particularly being applied in developing countries where the users don't actually have the finances to be able to buy equipment, and they don't also have the equity to be able to get loans. So cooling as a service is actually looked on as quite a positive model for low and middle income countries. There's also the integration of renewables more into the grid, and there's lots of opportunities for people in the food cold chain to apply solar panels or wind turbines. For example, in cold stores, the roofs are often flat, and there's huge opportunities to cover them in solar panels, which is often done. And there's opportunities for sharing of resources and facilities as well across the chain. One thing we have to remember is that we're not actually alone. There's a huge expansion in cooling in low and middle income countries. And access to the grid is an issue. Often in some of these countries, diesel gensets are used to provide refrigeration. And we need to make sure that the countries that are now starting to use more cooling don't make the same mistakes as we've made, and that we help them and ensure that the best low carbon technologies are applied. And this is something that we're involved in something called ACES, the African Centre of Excellence for Sustainable Cooling, which is partly funded by a number of governments, including ours, to try and make sure that the countries, but this one particularly in Africa, take up the best low carbon technologies. Sorry, I'm going a little bit over time, so I'll rapidly finish. So basically, to conclude, the significant challenges to reduce emissions. We need to also be very careful that we don't export our emissions to other countries, and we do our best to help them make sure that their cooling is low carbon. So thank you very much. Very happy to take some questions, and thank you very much for inviting me along to the event.
Thank you, Judith.